Hello friends, welcome to ACE Tutorials. In previous lecture, we have discussed effect of input type and magnitude on steady state error. In today's topic, we'll discuss effect of change in open loop transfer function g of s into h of s on steady state error, or we can say effect of type of a system on steady state error. Type of a system means number of poles at origin of Laplace transform of open loop transfer function g of s into h of s. You have to make a note that type of a system is determined by the open loop transfer function g of s into h of s, not by the closed loop transfer function g of s by 1 plus or minus g of s into h of s. The open loop transfer function of a feedback control system can be expressed in time constant form or pole zero form, that is g of s into h of s open loop transfer function is equal to gain k into zero term tz1 s plus 1, the second zero term tz2 s plus 1. In this way, more number of terms can be considered depending upon the system. In the denominator, you can see that s to the power n, s determines the pole at origin, the power n determines the number of poles at the origin. And the second pole term tp1 s plus 1, tp2 s plus 1. In this way, more terms can be considered based upon the system. You can see that the s to the power n value here determines the type of the system. That means type of a system means number of poles at origin of Laplace transform of open loop transfer function g of s into h of s. You can see that if n is equal to 0, type 0 system, n is equal to 1, type 1 system, if n is equal to 2, type 2 system. Example for type 0 system, where you can see s to the power n value for type 0 system we have considered as s to the power 0, then it can be considered as type 0 system. For type 1 system, you can see the n value we have considered as 1, then it can be considered type 1 system. In third example, type 2 system, where the n value is 2, therefore type 2 system we have considered. For example 4, type 3 system, you can see that the n value here is considered as 3. So by looking into this, we can consider this as a type 3 system. Let us see how this type of this system is going to affect on the steady state error. Analysis of type 0, type 1 and type 2 system. Here I have considered three types of the system: type 0 system, type 1 system, type 2 system. And I have considered the standard test signals as step, ramp and parabolic. In all the three conditions, I have taken the standard test signal as an input, that is step, ramp, parabolic for type 0 system, and even for type 1 system I have considered the standard test input signals step, ramp, parabolic, and for type 2 system also I am considering the standard test signals step, ramp and parabolic. Let us see type 0 system. As you know that for type 0 system, g of s into h of s is equivalent to k into tz1 s plus 1 into tz2 s plus 1. Numerator values are 0 terms, and in the denominator you can see the pole terms. For type 0, s to the power 0 into tp1 s plus 1 into tp2 s plus 1. By rewriting this equation, we will get g of s into h of s is equivalent to k into numerator terms and denominator terms. Let us see by applying step input for type 0 system, what will be the steady state error? For step input, positional error coefficient Kp is equivalent to limit s tends to 0 g of s into h of s. When we substitute limit s tends to 0 in this g of s into h of s, we'll get k value. When we substitute limit s is equal to 0, 0, 0, 0, then we'll get the value here k, which is nothing but Kp is equivalent to k. Therefore, the steady state error we know for step input ESS is equal to a divided by 1 plus k is equivalent to a divided by 1 plus Kp. For step input type 0 system, we are getting some finite error. You can see the step response after passing through certain transient period, we are getting a steady state output with steady state error. Finite error ESS is equivalent to a divided by 1 plus Kp. Let us see for ramp input. When we apply the ramp input for type 0 system, we'll see what steady state error we are going to get. Here for ramp input, Kv velocity error coefficient is equivalent to limit s tends to 0 s into g of s into h of s. As we know that g of s into h of s for type 0 system is this one. That means when I apply the limit s is equal to 0, anything multiplied with 0 is 0. Here we are getting velocity error coefficient is equivalent to 0. Therefore, we know that steady state error is ESS is equal to a divided by Kv, where Kv value is 0. That means a divided by 0, anything divided by 0 is infinity. You can observe here for ramp input for type 0 system, we are getting steady state error as infinite. So you can see the response. This is the ramp response. After passing through certain trans period, the error is infinite. That is ESS is equivalent to infinity. For parabolic input, you can see here acceleration error coefficient Ka is equivalent to limit s tends to 0 s to the power 2 into g of s into h of s. As you know that g of s into h of s for type 0 system is this value. When we substitute here and when we apply the limit s tends to 0, anything multiplied with 0 is 0. So therefore you can see that for parabolic input, the steady state error ESS is equal to a divided by Ka, and this will be equal to a divided by 0. Ka value is 0. So anything divided by 0 is infinity. You can observe here for for parabolic input type 0 system is giving infinite steady state error. Let us see the second example, type 1 system, where g of s into h of s is equal to k into tz1 s plus 1 into tz2 s plus 1 divided by, for type 1 system, s to the power n value is 1 into the other pole terms are tp1 s plus 1, tp2 s plus 1. Here, as I said, for analyzing purpose, I have considered two terms in the numerator and two terms in the denominator. These terms depends upon the system, and as per that we will get the number of numerator terms and denominator terms. And you can see that I am rewriting this type 1 system as g of s into h of s is equivalent to k into numerator terms and s into denominator terms. Let us see, by applying step input to type 1 system, what will be the steady state error. As we know the formula, positional error coefficient Kp is equivalent to limit s tends to 0 g of s into h of s, and this time g of s into h of s value for type 1 system is k into numerator terms and divided by s into denominator terms. When I am applying limit s tends to 0, anything divided by 0 is infinity. So therefore for step input for type 1 system, Kp is equivalent to infinity. Therefore steady state error is equivalent to a divided by 1 plus Kp is equal to a divided by 1 plus infinity. Anything divided by infinity is 0. You can observe here for step input type 1 system, we are getting steady state error is 0. You can see here in the response, this is the step response where the output, when it passes through the transient period, it reaches to the steady state, where you can observe here the error is 0. Type 1 system, for step input we are getting 0 error. When we apply ramp input, then you can observe here the formula velocity error coefficient kv is equivalent to limit s tends to 0 s into g of s into h of s. This time when I substitute this g of s into h of s value, this s and this s get cancelled, and when I apply the limit s is equal to 0, I am getting a constant value k, which is nothing but kv is equivalent to k. Therefore, for ramp input, steady state error ESS is equal to a divided by k is equivalent to a divided by kv. You can observe here I am getting here some finite error for ramp input type 1 system. After passing through certain transient period, you can see that output we are getting here actual output, that is steady state output with finite error. Next, for third example, that is for parabolic input, when we apply the parabolic input for type 1 system, we know that acceleration error coefficient Ka is equal to limit s tends to 0 s to the power 2 into g of s into h of s. This time when I consider for type 1 system g of s into h of s, in this case this power 2 and s get cancelled, and left out will be s into g of s into h of s. If I substitute s is equivalent to 0, so anything multiplied with 0 is 0, therefore Ka is equal to 0. In this, the steady state error is equivalent to a divided by Ka. So we know that Ka is 0, that means a by Ka is equivalent to a divided by 0. Anything divided by 0 is infinity. You can observe here in this second example, that is type 1 system, when I am applying parabolic input, I am getting some infinite error. You can see the response. This is the parabolic response. After output passing through a transient period, it reaching to a infinite error. The output is reaching to a infinite value. So looking into that, you can see that the steady state error is infinity. Third example, type 2 system, you can see that g of s into h of s is equivalent to, for type 2 system, the s to the power n value is 2. All other numerator terms and denominator terms as I have discussed in the previous example. Now let us see, I am rewriting this type 2 system. G of s into h of s is equivalent to k into t z1 s plus 1 into t z2 s plus 1 divided by s to the power 2 for type 2 system into tp1 s plus 1 into tp2 s plus 1. When we apply step input for this type 2 system, as we know the formula, positional error coefficient Kp is equivalent to limit s tends to 0 g of s into h of s. When I consider g of s into h of s, this type 2 system, you can see that anything divided by 0, when I substitute s is equal to 0, anything divided by 0 will get infinity. So that means here positional error coefficient Kp is equivalent to infinity. Therefore, steady state error ESS is equivalent to a divided by 1 plus Kp is equivalent to a divided by 1 plus infinity. Anything divided by infinity is 0. You can observe here for step input for type 2 system, we are getting steady state error 0. So you can see for the step input, the output passes through the transient period and then reaches to steady state, and in this case you can see the steady state error is equal to 0. Second example, for when we apply ramp input for type 2 system, as we know the formula, velocity error coefficient Kv is equivalent to limit s tends to 0 s into g of s into h of s, where we know that g of s into h of s for type 2 system is this s and power 2 get cancelled. So anything divided by 0, we know that infinity. Therefore, for ramp input, Kv is equivalent to infinity. the steady state error A is equivalent to A divided by K is equivalent to A divided by KV, where KV value is infinity. By substituting that, A divided by infinity is 0. That means anything divided by infinity is 0. In this you can see that for ramp input we are getting 0 steady state error. You can see that this is the ramp response output signal after passing through a transient period, it reaching to a steady state error, and in this case the steady state error is 0 for type 2 system. Third example, when we apply parabolic input for type 2 system, we know that the acceleration error coefficient Ka is equivalent to limit s tends to 0 s to the power 2 into g of s into h of s. G of s into h of s for type 2 system is this one. We are having s to the power 2 divided by s to the power 2, which going to get cancelled, and we are going to get these terms, and when we apply limit s tends to 0, we will be getting k value, which is nothing but k is equivalent to k. Therefore steady state error is equivalent to A divided by Ka. You can see here in this, for type 2 system, for an parabolic input we were getting steady state error, finite error, that is A divided by Ka. You can see this is a parabolic response. After passing through a transient period, the output is reaching to steady state error, where we are getting steady state error as a finite value. ESS is equal to A divided by Ka. In all these three examples, you can observe that as the type of the system is increasing, error is decreasing. You can see for type 0 system, for step input we were getting finite error, and type 1 system, for step input we were getting 0 error, in this case finite error, and in this case 0 error. And for type 2 system, for step input we were getting 0 error, in this finite error, 0 error, 0 error. So one thing we are understanding here, as the type of the system is increased, the error is decreasing. This is for step input. The same way you can observe for the ramp input. For type 0 system, here we are getting infinite error, and as the type of the system increases, for ramp input we are getting finite error, and in the third case we are getting, you can see that 0 error. First for ramp input type 0, infinite error. Type 1 system, for ramp input finite error. Type 2 system, for ramp input 0 error. So you can observe here the error is decreasing as the type of the system increasing. In third case, you can see for parabolic input type 0 system, error is infinite. For parabolic input type 1 system, error is infinite, and as the type of the system increased for parabolic input, here we are getting finite error. So this is the effect of type of a system on steady state error. So further we'll solve some problems. You should remember that whenever the problem is asked type 0 system, for type 0 system comes positional error coefficient constant value, velocity error coefficient 0, axillary error coefficient 0, and steady state error some finite value, and steady state error infinite value, steady state error infinite value. These are certain values need to be remembered whenever you are solving some problem for type 0 system. The same way, when you are solving problem for type 1 system, then you should know that positional error coefficient you should get infinite, and velocity error coefficient you should get constant value, whereas acceleration error coefficient you should get 0, whereas steady state error for step input 0, for ramp input some finite value, and for parabolic input infinite value. 0, finite and infinite value when type 1 system is considered. The same way, when type 2 system problem is asked, you should know that positional error coefficient you will be getting some infinite value, and velocity error coefficient you will be getting some infinite value, and acceleration error coefficient you will be getting some constant value. Looking into that, this error coefficient's value, steady state error for step input you will be getting 0, For ramp input, you'll be getting steady state error 0, whereas for parabolic input, steady state error you'll be getting some finite value. So these are certain effects of type of a system on steady state error. Hope you understood this video. For more such videos, like and subscribe my channel. Thank you.